I just got a new data set of a map of the cosmos that has 20 variables in it. There's gas density and dark matter density, stars, temperature, pressure, velocity. How can I decide which of these variables to visualize? Before I visualize them and decided which ones are the best to visualize? This sounds like a chicken and egg type of problem. When you get a new data set, you want to be able to quickly and easily explore the data so that you can make decisions like which variables to visualize, how to threshold them, how fast to play back the time steps, where are the interesting parts happening so you know where you should focus your camera. Data exploration is a critical step that lets you gain insight into your data. If your data files are large, it might take minutes to load in a single time step, or an hour to render a single image. It's not very easy to get a first look at your data or get a sense for how the data evolves over time at this rate. You can put together a quick and dirty interactive visualization called a previsualization, or Previs for short, to help you explore your data. Interactive computer graphics are rendered quickly enough that they can respond to adjustments in real time, like a video game, for quick iteration and decision making, so you can try out different variables, transfer functions, or camera positions. To make your previsualization interactive, you'll likely need to reduce your data file size so that it's small enough to fit into temporary memory. Subsampling is a great way to do this. Subsampling involves deleting a portion of your data, evenly throughout each data file. Volumes typically take up a lot more memory than simpler geometry like particles or surfaces, so it's usually best to convert your volume to particles, lines, or surfaces for faster loading. Once your data is small enough that you can play it back in real time, you can fly around your data to get a look at it from different directions, look at different variables, and change the playback rate to see if you want to change the timing of the simulation. Movies typically play at 24 frames per second. If you were to play your data at 24 time steps per second, you would need hundreds of time steps to get a visualization that only lasts a few seconds. If your data doesn't have hundreds or thousands of time steps, you may want to slow down the time step rate, and you can decide on that rate in the previs. It's okay if the downsampled data in your previs can't quite keep up with the 24 frames per second rate, but your camera absolutely must move interactively. The camera and the data can move at different rates. Moving around your data interactively as it evolves over time lets you not only choose interesting variables, but find when and where the interesting things are happening in those variables. If you have the ability to do pre-visualization in stereo 3D or in VR, this may be helpful. Stereo depth gives you more information when you're exploring your data, even if you aren't planning to render your final visualization in stereo. This is why at the NCSA, we do pre-visualization on a large stereoscopic 4K projection system. Let's take a behind-the-scenes look at a pre-visualization scene that registers several data sets and was used to design camera choreography for a documentary called Life, A Cosmic Story.
Here is another behind-the-scenes look at something that we created for the California Academy of Sciences for a planetarium dome show. And this was a journey flying into our Milky Way model, and then bringing up a supercomputing simulation of a turbulent molecular cloud that forms protoplanetary disks. And then we fly into one of those protoplanetary disks that will eventually be our solar system. That's what happens in the show. And so we created this, Stuart actually created this pre-visualization environment that integrates and registers the different data sets. We've got just a hint of our Milky Way galaxy with the galactic center up there, and then Earth is in here, and Orion and the Pleiades and Lagoon and Eagle Nebula. We've got our coordinates of where our other things are, and then this little sphere here is simply it's a background image of the galaxy in, is that radio, Stuart?
Or maybe
Far infrared, okay. So then as we go in here, we just simply have a background for the Milky Way, and yet another one for some reason. But here we used particles to represent this very large supercomputing simulation that was going to be rendered in volume rendering. It was an adaptive mesh refinement simulation. And we simply used particles here to give a sense of where it's located. And we can turn these things on and off and brighten different components. But essentially, the idea was to position this turbulent molecular cloud and orient it in such a way correlated with the position of what will be our developing sun that's inside of this pod that actually shows up in the simulation. And then actually inside of that pod, that here we're using Stewart's Mullian isosurfaces to represent this density value of where this protoplanetary disk is forming inside. And then we positioned our solar system in the proper angle with orbiting lines that represent the position of the planets. And then that was going to link up with the California Academy of Sciences next shot, where they just simply had today's solar system. So this is an example of a project where we're integrating multiple data sets. The colliding galaxy, the Milky Way galaxy, the turbulent molecular cloud simulation, and then actually another simulation of a protoplanetary disk inside there. And we have some very nice examples showing how these separate elements were rendered. But this scene was simply created to create this choreography. And I'm going to jump on the path back. And here we're actually diving into the plane of the Milky Way. You can sort of see the plane here. And we come underneath the plane. And this is another situation where we created an autoscale point at the location of the protoplanetary disk. You can see we're shrinking our scale as we're flying in. And we're viewing this in mono mode right now, but of course we were working in stereo. And here, the appearance of this supercomputing simulation that we're very careful. We bring it in very carefully in compositing so that you don't see the box outline. That's one thing that we do. We try to get inside the box. We try to hide the edges of the box, usually orient it in such a way where the edges are hidden or less pronounced, or fade off the edge of the box. Actually, we did too. And here you can see we even have a sense of which way the protoplanetary disk was spinning. And it wasn't going that fast in the end. It actually turns very slowly and very realistically. And we particleized a volume simulation, and then for each of the particles that took the data characteristics of the simulation, we created instanced volumes that have texture built into them to create sort of a realistic looking protoplanetary disk that you'll see in the movie.
Bob showed us a final previsualization setup that was used to create a camera path for this shot in particular, but we create a similar setup for every single visualization. Previsualization can help you at multiple stages of your pipeline to learn about your data, decide what variables to visualize, how to time your simulation, and how to move your camera. Fun fact: the word previs is also commonly used in the filmmaking industry, though it's used a bit differently there since it usually doesn't involve scientific data. Hollywood filmmakers will typically lay out an entire movie shot by shot with crude, simple 3D graphics. Then when they film the actual movie, they reference the previs to make sure the action and framing line up correctly.